Okay. Okay, so Dor Elboim will tell us about the interchange process and first passage percolation.
Thank you very much. Thank you all for coming. Right, so these days I'm spending most of my time working on two models in probability. The first is the interchange process, and the second is first passage percolation. And if you are interested in any of the questions that I will present here, please talk to me. Okay, so let's start with the interchange process. So the picture you should have in mind is a grid with particles on the vertices, where the particles interchange or swap randomly along the edges of the graph, like that. And I will give the exact definition in a second. Right, so here's the exact definition. You take a graph G, can be either finite or infinite. On each one of the vertices of the graph, there is a particle, a distinguished particle. And on each edge of the graph, there is an independent Poisson clock. So if you don't know what is a Poisson clock, it just means that each edge rings at random times. And if you run the process up to time t, each edge will ring on average t times and at random times. Okay, now what is the process? It's very simple. You have, if an edge E, which is UV, rings, then the two particles swap. The particle on V jumps to U, the particle on U jumps to V. Yeah, and then the particles start to mix like that. And what you get is a random permutation, pi t on the set of vertices that tells you for each particle where it ended up in this process at time t. Okay, so back to the example. You start running the process in time. Each one of these edges has a Poisson clock.
The Poisson clock have all the same.
Yes, all the same rate and independent of each other. Yes, thank you. Right, so you start running it. So the yellow particle jumps over there and then jumps again over there, and it keeps going, keeps mixing like that. And eventually what you get is this random permutation on Z squared, telling you that the blue particle starting over here ended up over there, the white particle starting over there ended up over here, and so on. Yeah, if you are worried about these Poisson clocks, this is, if the graph is finite, this is exactly the same as choosing a uniform random edge in the graph and switching. Okay, and one thing that you can do is study the cycle structure of this random permutation. So you can look at V, pi of V, pi of pi of V. So here you get a cycle of length 5. Here you have a fixed point of the permutation. And I think a natural question, and I will try to motivate it in a second, is whether all these cycles necessarily close. Like maybe they always return to the same vertex, and maybe you just get this infinite two-sided trajectory. So what do you think? Any guesses?
They all close.
Turns out it depends on the dimension. Okay. So the cycle structure of the permutation is of great interest. This was initiated around 30 years ago by Balintot and independently by Eisenman after Gale, Powers, who observed the connection between the emergence of long cycles in the interchange process on VD and phase transition in the so-called quantum Heisenberg ferromagnet. This is a well-studied model in mathematical physics. I won't get into that, but turns out it's related to this simple model that I've described. Okay, and in particular, around 30 years ago, Toth made the following conjecture. So here's the conjecture. You are doing this interchange process on ZD, okay, up to time t. And then you get the following behavior depending on the dimension. So the conjecture is that in dimension 2, no matter how long you will run the process, you will always have only finite cycles. And in dimension 3 and higher, the conjecture is that you have a phase transition. So there is some critical time, Tc, such that before this time, the cycles are finite, like 2 dimensions. But after this time, you will get infinite cycles almost 2.
Like a finite version of this conjecture for a finite grid where
yeah, you can state
cycles.
Yes, thank you. You can state all of this in like a finite big box, and then you will just ask that the size of the cycle tends to infinity.
The
cycle.
conjecture of how fast? Is this kind of,
This is actually, we are currently working on that. It should be actually that the cycles have a linear size in the volume of the box. So completely space filling inside the box. Please ask any more questions if is the model clear?
Cycle means something going to infinity.
Yeah, exactly. Just as 0, pi of 0, pi of pi of 0, and so on. It never closes.
And so infinite time it goes to infinity.
And what?
Infinite time going to infinity.
No. So okay, this is important to understand. Right. So in here, you want the process up to a finite time,
Yes.
and each one of the particles will just jump to a finite location. But then the cycle will be infinite. So after a finite amount of time, the cycle in this permutation will be infinite. Does that make sense?
I mean, they are arbitrarily the longest cycle.
No, so the cycle will be just infinite after that. That's the conjecture that in 3 dimension, you run it for some big finite amount of time, and then each particle will jump to some location. But when you look at v, pi of v, pi of pi of v,
Oh, sorry.
this will just never. Thank you. Okay, so let me tell you the heuristic for this conjecture. It's pretty simple. So in some sense, when you start looking at this cycle, it behaves somewhat like a random walk. So each time you jump to a random location, and it is well known that the random walk in 2 dimensions will be recurrent. So you will return to the origin with probability 1, and then in high dimension it will be transient. So with positive probability it will escape to infinity, and that's the heuristic.
So then why is there this T less than TC?
Right, so there is an obvious constraint, like, okay, when T is small, it cannot be, this is well known that when T is small, it cannot be infinite. So it's not really a random walk. Okay, so since the work of Toth, the cycle structure has been studied extensively, and in particular, the emergence of long cycles has been shown on many graphs, like the complete graph by Berestiki, Duet, Ram, Cosma, and also on trees, the hypercube, Hamming graph, random regular graph.
Wait, sorry, long here means infinite.
So on infinite trees, it means infinite. On finite graphs, it means long, like contain linear amount of the vertical. Right, not very well defined. But however, no similar results for ZD, and in particular, no progress toward the original conjecture of Toth. So here is the result that we proved last year together with Ellen Sly. So we showed that if the dimension is at least 5, and you run the process for sufficiently long amount of time, then the permutation will contain infinite cycles, almost surely. Right, so the conjecture is that in 2D it always closes, and we show that in 5D, after a long enough time, it will never close. Like you will have some infinite cycle.
Is sufficiently large explicit or is sufficiently large?
Yeah, but it's pretty bad. It's I don't know, e to the 100D, or but finite when. Right. So can you imagine this process in 5 dimensions?
So what's so special about 5? Why it works so?
Yes, so thank you. So this is something that we need for, so the proof is some sort of a multi-scale induction where you show that the cycle behaves like a random walk on larger and larger timescales. And then you basically, to do this, you concatenate independent chunks of cycles together. And for that, you need to use the fact that in 5 dimensions, it's no longer true. Right, and as I said, it was well known and it's very easy to show. It's basically some percolation argument that if you run in any dimension, if you run the process for sufficiently short amount of time, then you will only see a finite cycle. Okay, any questions up to here about the model or the?
Is there some obvious monotonicity, meaning that if you have infinite cycles for some t, you have for all larger t, or?
No, no. So actually, so our result prove the existence of a critical time. It's possible that you have finite cycles, then infinite, then finite again, then infinite.
These conjectures were verified computationally?
That I don't know.
I mean, you can just run this process. On a big enough grid, we see that.
Right, so I guess someone did it, I don't know. Yeah. I didn't.
Is there a conjecture for D equals 1?
So for D equal 1 for any time, it will be fine. It's basically, so you basically consider the set of edges that rank at least once, and this is a percolation. So no matter how long you run it, you will have finite components.
Is it clear? It's basically the dimension which matters, that if you have some little more graphs, but not going more adverse, but not going more some distance, you will have the same, like an hexagonal.
If you do it on a slightly different graph.
Yes.
So in the proof, it shouldn't matter. It's pretty robust. Right, so there are many open questions. I'm trying to do it in 4 dimensions now, but it's much harder. And then you can do it in finite volume and the quantum Heisenberg ferromagnet. Right, so these are the kind of things that I'm working on currently. So now let me move on to the second half of the talk, which is completely independent. And this is first passage percolation. It's a model of random geometry, and maybe a bit related to the first talk that we heard today. Okay, so what is that? You just consider a graph, let's say z squared. On each one of the edges E, independently there is a random weight distributed according to some distribution F. So pick your favorite distribution, say uniform between 0 and 1. And then sample the weights on the edges independently according to this distribution. And then this gives you a weighted graph. So just study the shortest paths in this weighted graph. Okay. So for any pair of points x and y, you define the passage time, which will just be the minimum over the paths of the sum of weights along the paths. Connecting x and y. Right, so let's have a simple example here. Each edge has a random weight. You take 2 faraway points. It's always interesting asymptotically. And then, you just have the shortest path. So the sum of weights along the path connecting the points is minimal. Right, so you can maybe think about it as a network of roads where each road takes a random amount of time to cross due to traffic. And then you want to get all the way to N0, so you open the navigation app and it tells you this is the path that you should follow. And this is called the geodesic. So there are many conjectures about this. Not a lot is known about this model. So if you take Tn to be the passage time between 0, 0 and N0, it sort of makes sense that it goes linearly with N. So this is known. And it's also known that you have this asymptotic time constant. So if you divide Tn by N, it will converge to some constant, almost surely. But then I guess the biggest conjecture over here is that the variance of the passage time will go like N to the closer. So this is like less fluctuative than sum of independent variables, which has a linear variance. Because here you sort of also minimize over paths. So it makes the variance of the passage time smaller. And then you also have some conjectures about the geometry of this geodesic, like how far it is from being just a straight line. The conjecture is that it's a borderline to the truth. But today I want to talk about a different phenomenon, and this is the phenomenon of coalescence of geodesics. So here it's, so you look at one geodesic, let's say from 0, 0 to N0, and then you also look at another geodesic from 0 edge to N edge. Turns out that what you will see with high probability is that these two geodesics coalesce, meaning that they will intersect and proceed together for the entire way. So back to the analogy with roads, So suppose I want to get from Princeton to New York, and then you want to get from Trenton, which is close to Princeton, to Newark, which is close to New York, then we will both take the highway. So this is saying that you create this kind of random highways. Okay, so together with my colleagues, we showed that this is indeed the case. We proved we have some quantitative version of this result. So this is under some mild assumption on the edge distribution F, you can show that as long as H is not too big compared to N, then these two geodesics will coalesce. If H is less than N to the 1/8, then they will coalesce with high probability. So this is like the symmetric difference between the two geodesics will be little O of N, or will have little O of N. So high probability means that probability tending to 1 as N tends to infinity. Okay, any questions about that?
So how many times they get together and diverge again? Like, is it one big chunk or?
Yeah, so we assume that the distribution is continuous or something like that. And then it cannot happen because between 2 points, you will always have a unique geodesic. So if they intersect over here and intersect over there.
It has to be one.
Yeah, exactly. Right, let me show you some simulations. I just sampled the weights in the computer and computed the shortest paths. So as you see, they coalesce. Yeah, here it didn't work because it's just high probability sometimes. Okay, in the last 2 minutes, let me talk about some other question that I really like. And this is the PKS midpoint problem after Binyamin, Nikolai, and Shram. And it's the following very simple problem. So you take the geodesic between minus N0 to N0, 2 faraway points, and then simply show that the probability that the midpoint, the origin is inside the geodesic, tends to 0 as N tends to infinity. So it sounds almost trivial, right? Like, why would the geodesic go exactly through the midpoint? But this was open for like 20 years or so. Eventually, it was solved by Albert Hoffman, but it turns out it's very much related to this coalescence phenomenon that I told you about. And actually, our methods allow us to prove some quantitative bound. So something that decays a polynomial with that.
Do you have some understanding of how far away you can go from the straight line? So
Yeah, it's related to the transversal fluctuation exponent, but it's not exactly the same. Yeah, because maybe it fluctuates, but still it has like 3 points where it passes.
but do you know how much it fluctuates?
So the conjecture is n to the 2/3, and it is known up to n to the 1/3. Okay, so by the way, the midpoint, there is nothing special here about the midpoint. Like any vertex, as long as it's not too close to the endpoints of the geodesic, you expect the probability to pass through to 10 to 0. Okay, and so all of this story was just in 2 dimensions. Of course, you can do this in higher dimensions. So it turns out it's even the model is even less understood in higher dimensions. And in particular, the midpoint is still open in 3 dimensions. It sounds weird, right? You have even more space, so it should be easier to say that it doesn't go through. But you have some advantages in 2 dimensions later. So this is a question that I really like and try to solve, but so far we couldn't. Something that we could show is that you only have constantly many exceptional vertices. So basically you fix some epsilon, and then you look at no matter how long the geodesic is, you look at the set of vertices for which you have a probability epsilon to go through, then this will be at most 100, or no matter how long the geodesic will be. Yeah, so yeah, I guess I'll finish.
Questions?
So in your second result, is this exponent 1/8? Is it optimal, or what do you expect the optimal exponent?
So you expect it to be like the transversal fluctuations, like how far you get from the straight line. So n to the 2/3 should be the right answer.
Can you heuristically motivate that 2/3?
So all the conjectures come from a certain integrable version of this model. So it turns out if instead of first passage, you take last passage percolation with some very specific weight distribution, which is exponential, then you can compute everything that you want. You can prove all of these conjectures. And then the conjecture is that it's all universal. In this integrable case, it's related to a lot of other problems, determinantal process and some algebra.
Do you expect some, once you renormalize your shortest path, to have some convergence?
Yes.
What kind of process?
So it's the so-called KPZ universality class. It should converge to something called the directed landscape. But the distribution of the passage time will be trace Widom distribution after normalizing, and it's very much related to the largest eigenvalue of a random matrix.
Okay, let's thank Dor again.